Hi, I'm Carla, and today, along with Mateo, I'm going to talk to you about Hummingbird, an open source library from Gray Systems Lab at Microsoft. And this was developed along with several collaborators from the open source communities in PyTorch and TVM. Hummingbird is a library for machine learning prediction serving. But first, I'll go a little bit into an overview of what that means. So when you're getting started with machine learning, you have a bunch of data. You want to perform some learning, some training process, which will then output a model. Once you have the model, you're ready to deploy that model to some sort of server and serve that to a bunch of users. The second part where this prediction serving is happening, that's the focus of Hummingbird. So this prediction serving and modeling serving will be what I'll be referring to today versus the initial phase, the training phase. When we got started looking at this model serving, we did a survey of what systems already exist in practice today. And there's a lot of specialized systems that have been developed, such as Onyx Runtime, TensorRT, and TVM. And we noticed that a lot of these systems focus on deep learning, or DL. And there wasn't nearly as much in the space of traditional machine learning methods. It's largely overlooked. So for example, scikit-learn, ML.NET, and H2O.ai. To talk a minute about what traditional machine learning is and why it's important, I have this graph here from a Kaggle survey. And this survey asked a bunch of machine learning professionals and data scientists what sort of models they use in their work these days, and kind of a survey overview of the broader space of the model. And in green here, the graph in green, you can see linear logistic regression, decision trees, random forest, gradient boost, and Bayesian models. These are all examples of traditional ML models. And so they're very prevalent everywhere and very important that we make sure to optimize as much as possible. And another data point, in a Microsoft survey, we gathered a bunch of open source Python notebooks on GitHub and compared across 2 years which libraries were the most imported. So the first few winners there are mostly data manipulation libraries. And in fourth is scikit-learn, which is one of the main traditional ML model frameworks. And it grew a lot between these 2 years, and it continues to grow a lot today, versus, say, TensorFlow, which is 7th, or PyTorch, which is 12th, not pictured. In the neural network space, they're still growing and still up and coming, but it's very important that we are able to optimally support scikit-learn and traditional ML models. So the problem is the lack of optimizations for traditional ML serving. These systems for training ML models are not necessarily optimized for the serving part. And this is because ML models, the traditional ML models, are expressed using imperative code in an ad hoc way. So it's very difficult to kind of do an even generalization in a way to optimize them using a shared logical abstraction. And because of this, these traditional ML models cannot easily natively exploit hardware acceleration. So across a lot of these traditional ML frameworks pictured here, if I wanted them to run on a particular piece of hardware, I'd have to write specialized code for each of the operators across each of the frameworks for each hardware system. So it doesn't really generalize well, or it doesn't really extend or easily scale. To understand a little bit more about why, we're going to take a quick look about how traditional ML models look on the inside. So on the left here, I have a data frame. I have 2 categorical features, A and C, and then 2 numerical features, B and D. And I'm going to feed them into my traditional ML model, which currently is a black box. The example here is of a binary classification. And you can see on the right, I have a 0 versus 1. I expect that to be my output. So looking inside we have a DAG, a directed acyclic graph of operators. You may have heard this as called as a pipeline. On the left, there's a bunch of featureizers, which are going to do some processing of the data. And on the right, we have the predictor, which is going to actually output the prediction. Stepping through this for a second, we have, first, what we're going to do is split the incoming data into categorical features and numerical features, where the numerical features will go to the top node and be normalized with this scalar, and the categorical features will be one-hot encoded in a way that they can be easily processed in hardware. And then we'll concatenate these 2 vectors together, merge them back, feed that data into the final score to compute the final score, the logistic regression. So this is just one very, very simple example of what a model might look like. Across all of the traditional ML frameworks, there's hundreds and hundreds of these featureizers and predictors. And so it's kind of hard to represent them in a concrete and a way that makes sense across all of the different frameworks and all of the different options. We contrast this with deep learning. In deep learning, we primarily rely on the abstraction of tensors, and tensors is very basically just a multi-dimensional matrix. So if we look inside a deep learning model, deep learning models are also expressed as a DEG, but specifically focused on tensor operators. So here you can see I have this very generic matrix multiplication, addition, those sort of mathematical operations that are easily represented across a wide variety of systems. And the people that built these systems for deep learning prediction serving are able to capitalize on this, the fact that we're using tensor operations, and exploit that abstraction to work across lots of different target environments. So at the top here, I have, for example, PyTorch, TensorFlow, just to name a few. And I'm able to take that and compile them down into this prediction serving framework. And from there, easily convert that to my target hardware, such as GPU, FPGA, TPU, that sort of framework. And so the benefit of this is tensors and the tensor operations are efficient, implemented very efficiently. And so we have that as a huge plus. And it's due to the fact that these tensor operations are declarative. It's powerful enough to detach how you express the neural network from how you execute it, which allows the compiler to do some additional optimization. And this gives us seamless hardware acceleration. So I can just write my model in PyTorch and then kind of target that to run on any target hardware. And so from this, we claim we reduce engineering efforts because we very simply are able to write once and kind of run anywhere. So putting this back into the broader picture, where I see at the top the traditional ML frameworks that I talked about earlier, we're not able to immediately run those. So for example, if I have my scikit-learn model, I'm not able to run that natively for prediction serving on GPU. I have to do something additional. And this is where Hummingbird comes in. Hummingbird is able to translate or compile these models into a tensor-based framework, which allows us to leverage these existing tools in the deep learning space. And next, Matteo is going to tell you a little bit more detail about exactly how that works.
Thank you, Carla. And let me explain you how Hummingbird internal works. So our observation is that pipelines are actually composed by two classes of operators. So one is algebraic operations. Think about like linear regression, where you basically are doing a bunch of matrix vector multiplications. And the second class of operations that are algorithmic. For these operations, think about random forest or one-hot encoding, where you basically where you basically have to implement an algorithm for doing, for instance, a tree traversal. So as you can imagine, translating algebraic operations into tensor is actually straightforward, because basically you just use the tensor linear tensor abstraction to kind of implement the matrix vector operations. Regarding the algorithmic operations, instead, these are more complex. This is because algorithmic operator, they basically implement arbitrary control flow patterns and data access patterns. So our solution to solve this specific problem is to try to introduce redundancy, both at the computational storage level, such that we can more easily target the tensor abstraction. And while we do this, we basically try to have different implementations for each of these single operations, such that we can target a specific implementation based on the statistic of the trained algorithm. So I imagine that this looks a little bit too high level, so let me go over an example with you. So here on the left, you can see a simple decision tree. In this decision tree, we have 4 internal nodes and 5 leaf nodes. And we are basically using 5 input feature to do inference over this decision tree. So let me explain you how Hummingbird is able to do inference over this decision tree. So Hummingbird uses 4 data structure. So the first two are the matrix A and vector B. So the matrix A basically encode. You basically have one column for each of the internal nodes and one row for each of the features. So basically, matrix A is used to basically encode which feature is used by which decision node. So that means that if you look at the first row, it basically means that the first decision node will use input feature number 3. The second decision node will use input feature number 2, so on and so forth. Then the vector B is just basically storing the threshold, one for each of the decision nodes. Then you have other two data structure. Matrix C is used to basically encode given a node, the path in order to reach a leaf node. So in C, we basically have one column for each of the 5 leaf nodes in this example, and one row for each of the decision nodes. So if you look at the first column, basically, this is telling me that in order to reach leaf node 1, I have to go left for decision node 1 and left for decision node number 2. So 1 here basically say go left, while -1 means go right. If you see the column number 2, instead this is for leaf node 2, basically it's telling me that I have to go left 1 and right 1. Then for the 0 basically means that we don't use that that specific node in order to do this traversal. Finally, the vector D is basically encoding the path in order to reach a specific leaf node. So we have one column for each of the leaf nodes, and the way in which we are coding the path here is basically just summing up the number of 1. So in order to reach the leaf node number 1, we basically just have 2. So we basically just sum up the 2 ones. For leaf node number 2, we only have 1, so on and so forth. So now that I introduced this data structure, let me go over the actual algorithm. So we start with matrix vector multiplication between the input features and the matrix A that was encoding the way in which the decision node used the input features. And the output is a vector that basically contains the specific position which the feature are used. Then we basically do a simple comparison between this vector with the feature with the threshold that we store in the vector B. And this is basically telling us which are the decision nodes that are actually triggered given these input features. So in this case will be decision node 3 and 4. Then we use this vector and we multiply it with the matrix C to basically evaluate the path to reach the leaf nodes. And then we do a comparison between the path that we generated by doing this matrix multiplication with the path that we computed and stored into the vector number D. In this case, in this comparison, the only leaf node that have 1 is leaf node number 4. So that means that for the input feature that we used, the leaf number 4 is the final result. So of course you can I explained this example with a simple decision tree, but you can assume that for the same algorithm also works if you have tree ensemble, and basically we do this by batching all the trees together. So one interesting things about this approach that we call GEM, because it exploits the generalized matrix multiplication implemented in the tensor runtimes, is that we're basically evaluating all the decisions and all the leaf nodes, all the possible paths to reach the leaf node all together. So that is what I meant when I say the computation redundancy. So if you think about this, this is kind of strange because we are basically are saying that we are doing exponentially more work than you will do when you usually implement your regular decision tree traversal algorithm. But the interesting part is that since we can map this to a matrix vector multiplication, we can exploit the massive parallelism that is coming that we have in the modern hardware, and this allows us to achieve actually really good performance. Of course, this kind of algorithm won't work in all the cases. Specifically, if you have like a really deep tree, this won't work because you're doing a lot more comparison than in the optimal case. And in fact, in Hummingbird, we actually have other 2 different tree implementations. So one that we use that is called a tree traversal that we use when the trees instead are more deep. And instead there is another one that is called a perfect tree traversal, which instead we use when the trees are more like a bashy shape. Let me go over this two algorithm really quickly. So for the tree traversal method, we store the information of the tree using 5 different vectors. The first vector basically store all the left node IDs. The right node IDs are stored in the second one. Then we store the feature IDs in the third one, the threshold values in the fourth vector, and the labels ID for in the last vector. And in all these vectors, we basically have one column for each node that we have in the decision tree. So in this decision tree that we use as example on the left, we have 8 nodes. So that means that this vector basically that have 8 columns. How you read it is if you start with the column 0, we basically say that if for node number 0, if you evaluate the condition and the condition is true, you go left, and you need to, the next node that you need to evaluate is node 1. If instead you go right, the next node that you need to evaluate is node 2. In order to evaluate node 0, you basically have to take the feature ID with ID number 3, and the threshold that you will be using is 0.5. And in this data structure, we use -1 if a specific value is not used. For instance, since for node number 0, this is a decision node, we have -1 for the label because there is no label attached to this node. Now let me go over on the algorithm in this case. So we start with the root node, which is the node number 0. What we do is we look at the feature ID, at the vector containing the feature ID, and we gather the feature ID at the column 0. Then using this feature ID, we gather the actual feature from the feature vector. Then we do another gather operation for picking up the threshold, still related to the node 0. Then we basically have at this point all the values that we need. So we do evaluation between the feature and the threshold that is stored in the tree. And then we use the where tensor operation to basically say, okay, if the condition is evaluated to true, do a lookup over the left vector, otherwise do a lookup on the right vector. And this is basically telling us which is the next node that we have to look at. So we basically repeat this algorithm until we reach the max depth of the tree. Related to the perfect tree traversal method, the algorithm is really similar to the tree traversal method. The only things that we do is that we introduce computational redundancy because we make the tree perfect. So this allows us to be a little bit more efficient on the algorithmic side, but we introduce, of course, redundancy at the storage level. So far, I only explained like 3 algorithms. Hummingbird actually support around 50 different algorithms, and we don't support just 3, but we support, for instance, linear model. We support some featureization such as one-hot encoding. We support PCH, etc., etc. So let me briefly introduce the high-level design for Hummingbird. So Hummingbird gets as input a trained model implemented either on scikit-learn. We support XGBoost, LightGBM library as well on extra time, and we recently also added a few operators on SparkML. So once that you pass the trained pipelines to Hummingbird translate these pipelines into tensor programs, and then you can run these tensor programs using one of the deep learning predictions serving systems. So for the moment, Hummingbird support exporting tensor programs into PyTorch and TorchScript, into Onyx Runtime, or into TVM. We are working on trying to add support for other input libraries such as ML.NET and H2O, and we also welcome contribution if someone wants to help us to extend the supported library also for the deep learning runtime such as TensorFlow and TensorRT. Let me give you some idea on the numbers that you can reach by using Hummingbird. So for this experiment that I'm going to introduce, I'm going to use an Azure NC6 machines with an Accelerators processor with 6 core, 112 gigabyte of RAM, and an NVIDIA P100 GPU. So for this experiment, we basically crawl the OpenML CC18 benchmark, and we basically got the 72 dataset, and we trained around 300 scikit-learn pipelines. And among all the pipelines that are inside this OpenCL benchmark, Hummingbird was able to translate around 80% of them. And for the performance that I'm going to show, we basically took the data set, do this, the 80-20 split, do the training using the 80%, and do the testing using the 20%, the remaining 20%. And for the numbers I'm going to show, we use the Torch script backend. So we export the model using Torch, and then we convert the Torch model using the JIT framework into a Torch script program. So let's start with the CPU numbers. So for the CPU numbers, we were able to accelerate around 60% of these OpenML pipelines. And in the worst case, we were around 60x slower than the original pipeline. But in the best case, we were around 3 orders of magnitude faster. If then we look at the GPU numbers, for the GPU, we were able to accelerate 73% of the pipelines. And in this case, we were, in the worst case, we are we are 2 orders of magnitude lower. And in the best case, we are still more than 3 orders of magnitude faster. So the slowdown is mostly due to the fact that we just kind of run all the OpenML pipelines, and some of them, they contain really sparse input data that that don't get any benefit by GPU accelerations, and some of the models were really small, like a decision tree with like 3 nodes, and in that case, acceleration provided by Hummingbird, the acceleration provided by Hummingbird doesn't help. And now it's time for a real demo for Hummingbird.
So as you can see here, we have our notebook set up, and the first thing that you need to do is you need to do pip install Hummingbird ML if you haven't already installed it. Here we have, so we'll skip it. And I'm going to also, for this demo, I have everything, my model pre-trained, so I'm going to need to import pickle to unpickle that. And highlighted is from hummingbird.ml import convert. This is the main function that we'll be using. For this demo, we're going to be using this year dataset, which predicts the year that a particular song was written in. And we're going to open the pickled data, load it up, and we're going to just print the shape of it. We see around 50K rows or so. And just a quick look at the data so we can make sure everything looks good. So now we have our data, we need to load the model. We have our pre-trained model. It's of, as I mentioned, light GBM. We have 500 estimators, and we're going to go ahead and read that model in and unpickle it, load it up. Okay, and the next thing we're going to do is we're going to time this model with light GBM. This will be CPU only because it only works for CPU. And in this demo, I have pre-typed all of the time it instructions. So I have the field that we're going to save stored, and then the time it instructions, but we're going to type the commands that are used particular to Hummingbird and prediction. So we're going to type light GBM, we model.predict, and predict over the data, and we're going to head and let that run. The time it function is going to run this a number of times, and we see that it's 800 milliseconds. And so, yeah, the mean plus standard deviation of 7 runs is what it shows. And so now, to demonstrate Hummingbird, we're going to convert this model to PyTorch. So we type model equals convert light GBM, we have model to torch in this case, and we can see that that gets loaded. Now we have our model, so we're going to first run this on PyTorch with just the CPU. And notice above we have the model.predict instructions. We're going to copy and paste that exact thing because the syntax is identical. So model.predict, and let it run. So we have 1.9 seconds. A lot of times PyTorch CPU will be longer. Sometimes it will be faster. It just kind of depends on the data set and the model, and also what underlying hardware you have. So now time to play with the GPUs. PyTorch provides this very simple instruction to switch from CPU to GPU, just model.to CUDA. This is a PyTorch command. That will switch the model, and so now we are ready to run with GPU. Again, we can copy and paste from above the model.predict of the data, hit enter, And so we have 48 or so milliseconds, so significantly faster than before. That's PyTorch. Now I'm going to show you our TVM, which is a compiled framework, so we're going to be able to get even more additional speedups. So we're going to start again with the light GBM we had before, and we're going to say model TVM equals convert. This time we're going to go to TVM, give the data. All right, and now again, very similar, exact same syntax, but we've called our model model TVM in this case. So model TVM.predict with the data. And at the end, I will show you a graph with all of these values, but this CPU time is faster than the PyTorch CPU time. Going to go ahead and try this out with TVM and GPU. So we're going to reuse the convert command. This time we're going to tell it to go to CUDA. And it will recompile everything, the model, to have the TVM model with GPU. And now we can reuse the same instruction. So around 23 milliseconds. All right, now to plot them all together, I have a plotting function. And you can see here the original time. The PyTorch CPU time is about twice as long for this particular model. Your mileage may vary, maybe sometimes faster, sometimes a bit slower. And then we see PyTorch GPU is 0.0484 seconds. And comparing that with TVM GPU, TVM is faster for both GPU and significantly so with CPU. So I encourage you to try out some of our notebooks and try them with your own models to see what results you get. Here is our GitHub. It's github.com/Microsoft/Hummingbird. And if you go there, you can check out some of our notebooks. Very similar to the examples that I just ran now. We also welcome users to submit their new notebooks and what models they find interesting. Also on our website, there's a little bit of an introduction, an explanation of how Hummingbird works, a lot of the stuff that Matteo went over, an installation guide working on Linux, Mac, and Windows, several examples, and we have documentation of our API. And you can also join our community on Gitter, and we're happy to have you provide feedback about features that you might want. We also have, if you go to our wiki, we have a list of the operators that we currently support across scikit-learn and like GBM, XGBoost, OnyxML, and SparkML. I encourage you to file an issue if you have some feature requests or run into some sort of a bug. We're happy to hear your feedback.
And that's our demo. Thanks for watching. Here's a few more additional updates that I want to leave you with. So far, we've reached around 21,000 polls on PyPy and 2.4 thousand stars on GitHub. Please hit us up. We've demoed this at Microsoft Ignite, and we've integrated part of Hummingbird with the Onyx converter tools. We also have an OSDI paper with a bunch of verified benchmarks and evaluations. And some of our newest features involve Pandas data frames, PySpark ML support, and TVM support. And I want to stress that we are very thrilled how much open source interaction we've gotten from community members. We have, of our contributors, all but 2 of them are outside of Microsoft. So we would love for you to file an issue, a bug report, a feature request, any sort of that thing. Please reach out. I'll leave you with our email address. And thank you very much for listening.